Hello students. In today's lecture we shall learn one method of speed control, that is Leonard method. Leonard scheme. We have discussed earlier that there are basically three methods of speed control: armature voltage control, field control, and armature resistance control. So this method, this scheme is actually implementation of armature voltage control. That is the most commonly used method of speed control. So for this we have this DC motor whose speed we want to control by armature voltage control method. This motor is supplying certain mechanical load. It's connected here, shown here. So, and this is the field winding which is given a fixed supply. So the flux, I have assumed that the flux of the motor is constant, and you have to vary the voltage across the motor Vm to vary speed of this motor. So we have learned that speed depends on voltage, that is proportional to voltage. If we change the voltage, speed will also change. So we have to actually vary this voltage Vm, and the current that is flowing here in the motor, this is the armature current Ia. This is a function of load on the motor, that is, it is proportional to the torque required by the load. So this current will vary as the load varies, and this current will be high current. Actually, is a power that is generated. This is taken by the motor, which is converted to mechanical power, and that is delivered to the load. So this current will be a high current, and that may also vary with load. So this means that the power supply here should be such that the voltage remains constant, independent of load on the motor. So for that we require a high power supply, so that the voltage here is stable, it doesn't fluctuate as the load on the motor is changed. So this means that we require a high power variable voltage DC supply on this side. So for this what is done in this scheme is that we supply this power from a DC generator, and the DC generator is run by some prime mover. So that prime mover is usually a three-phase induction motor. So this induction motor is coupled to this DC generator, and this DC generator is given a supply from here. So this prime mover runs the generator, and the voltage is available here, and this voltage is given to the motor whose speed we want to control. And the voltage here, voltage of the DC generator will depend on the speed, and it will also depend on the flux produced by the field winding. Speed of the DC induction motor will remain practically constant. This induction motor, you know that it is almost a constant speed motor. So speed will be basically constant. The flux you can vary. So but depending on the flux, the voltage will vary. So voltage of a generator will be proportional to the flux, which in turn will be proportional to the current in the field winding, or the voltage across the field winding. So this voltage, if you vary, it will vary the current in the field winding. This will vary the flux in the DC generator. That will cause output voltage of the DC generator. That will change the input voltage of the DC motor, and its speed will change. So this is the basic philosophy behind this scheme. And this actually, this is a generator, and the power flows through this three-phase supply, which is given to the induction motor, and this output power of this induction motor goes to the DC generator. This is actually input power of from the three-phase supply divided by efficiency of this induction motor. So this is the input power of this generator also. Output power of this generator will be input power divided by efficiency of the generator, and that will be equal to P in upon efficiency of induction motor multiplied by efficiency of DC generator. And this power will be again converted into mechanical power. So output power here will be input power divided by efficiency of this motor, and input power here is this the So overall it will come as P in upon efficiency of induction motor, efficiency of DC generator, and efficiency of DC motor. So efficiency of the system will be product of the efficiency of the three machines. Power flows through this machine, then this machine, then this machine, and then finally reaches the load. So output power will be much smaller than input power because of poor efficiency. Efficiency of each machine, suppose it is 80%, so 0.8 into 0.8 into 0.8. So it will be very low. So this is one of the drawbacks of this scheme. So how we do it? Now here the rating of all these machines will be power rating will be identical because same power flows through all the three machines. So this means that the power rating of all the machines will be almost identical. The power required by the field winding of generator is much smaller than the power rating of the generator. It is usually less than 1%. So the power requirement here is very small. So this means that on this side we can use a low power variable voltage supply. This supply cannot be connected directly here because here the requirement is that it should be a high power variable voltage supply. So here we can use a low power variable voltage supply. For small motors even you can make a potential divider using some rheostat. So rheostat is there and we have made it as a potential divider. The variable point is moved here and that will vary the voltage across these terminals. So by varying this, the field current of the DC generator will be varied and that will affect in the speed control of this motor. Here I have shown a variable or reversing key also. You can connect the terminals here for positive direction of field current and you can connect on the other side to have a negative flow of current like this. So you can easily change the direction of the field current by using this double pole double throw switch. So this scheme is that you have to vary the voltage here, and this I have shown one example that it is a potential divider. It can be a low power rectifier also, control rectifier, or you can get it from some low power DC converter. Any of the low power variable voltage supply can be used here to vary the voltage here. You vary the voltage, that causes the field current of the generator to vary. This causes the output voltage of the generator to vary. That causes input voltage of the DC motor to change, and that will change the speed of the motor. And power flows through all these machines. Now here you can see that this machine can work in all the four quadrants of a speed torque plane. Suppose we are having this direction, and in this direction the machine is running in the first quadrant as a motor, and if you want to have the second quadrant operation, if you recall the various quadrants of speed torque plane, speed torque. So the first quadrant where speed is positive, torque is positive. In second quadrant, speed is positive but the torque is negative. If you want to go in the second quadrant, what you have to do is you have to reverse the production of torque by the motor. So it will go in the second quadrant, or it will be working in the generating mode. So for this what you have to do, you have to make this voltage less than the back EMF of the motor. In the normal first quadrant operation, this voltage will be more than the back EMF and the power flows like this. If you reduce the voltage across the motor such that it becomes less than back EMF, then the current will flow in the reverse direction and we shall have the second quadrant operation. So how we can do it? You just reduce the field current here suddenly. Reducing the field current will change the output voltage of the generator. That will change the input voltage of the motor. So VM will become less than EM. As soon as this happens, current starts flowing in the reverse direction. This means that now this machine starts working as a generator. So the power flows from the mechanical system of the load, mechanical energy of the load and the motor will be converted to electrical energy, and this electrical energy flows back here, and this generator is now working as a motor. It absorbs power and converts this power into electrical energy, and this 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 starts behaving as a motor which converts this input electrical power into mechanical power. This mechanical power is absorbed by the induction motor, and this converts this electrical power into electrical power, and it is fed back to the three-phase supply. So this is the second coordinate operation, and we are having regenerative braking. So the energy stored in this mechanical system of the load and the motor is converted into electrical energy, and which is converted into mechanical energy by this DC generator, and then it goes to this motor which now behaves as a generator and converts this mechanical energy into electrical energy and feeds it to the three-phase supply system. So in that way you can have the second coordinate operation. For third and fourth coordinate operation, that is for reverse motoring and reverse braking, what you have to do is that you have to reverse the direction of flow of current in the field winding of the motor. If you change the switch connection like this, direction of current will change, polarity of the voltage will change, and we can now have third coordinate and fourth coordinate operation. In the case of motor, the voltage here will be more than back EMF, and you will have the third coordinate operation. For generating mode, you have to reduce the voltage here below the back EMF, so that we have the generating mode, that is the fourth coordinate operation. So in that way all the four coordinates operations are possible. Now let us see the advantages and disadvantages of this scheme. Advantages: number one, all the four coordinates operation is possible. As I explained here, we can operate the machine in all the four coordinates of speed, torque, plane. Regeneration is possible, that is, we can apply brakes and the mechanical power here will go back to the three-phase supply. So regenerative braking is possible here. Then another important advantage is that short duration supply disturbance does not affect load because of high inertia. Any disturbance here in the supply will actually try to change the speed of this motor, but this is a mechanical system, it has a high inertia, so speed of this motor will change slightly. That will cause a change in the voltage here, that will cause the change in the speed here. Again it will have inertia, so the whole system has a high inertia, so small disturbances here will not affect the speed of this motor because it takes time. This will respond to the disturbance here, and that will cause change in the voltage here, and then this will take its time to respond to this change in the voltage, and finally the load will face the problem of fluctuation. So this because of high inertia, the small duration disturbances here will not affect the load speed, and it will continue to run at a smooth speed. So small duration disturbances will not affect the performance of the load. So this is also advantage of this scheme. Now what are the drawbacks? Drawbacks, as you can guess here, it will have a high initial cost, because to run this motor we require two additional machines of same rating. Assuming that the cost of all the machines are equal, the cost will be triple the cost of this motor. So the cost of the drive will be high. and again it will have a very poor efficiency. As I explained here, it is the multiplication of efficiency of the three machines. So efficiency is very poor. Third drawback here is because there are three machines of identical sizes, it will be a large size and weight, and it will require more floor area. One machine is installed here, two additional machines will be installed at the same site, so the floor area requirement will be triple the original motor. So these are the drawbacks of this method. So drawbacks are so high, you might think that why at all it is used. So in earlier days we did not have the power electronic converters for high power applications, so there was no other means of speed control of in DC motor. So this was the only option. We had to use this scheme despite all these drawbacks. Whenever we required speed control of DC motor, we had to use this Leonard scheme of speed control of DC motor. But after the advent of power electronic converters for high power applications, this has been replaced by small converters which are thyristor based, which directly convert AC into DC. So these schemes which nowadays we use by using a control rectifier are known as static Leonard schemes. So this as you can say dynamic, or you can say moving parts are there. These are replaced by static devices, that is power electronic converters. We may have a control rectifier which is given 3-phase supply, or you may have some DC chopper with inputs DC supply, or you may have a combination of these converters, that is we have 3-phase supply, then we have a rectifier, and then we have a DC to DC converter, that is chopper, to get a variable DC supply here. So all these schemes we shall discuss in the upcoming classes. So this is what is known as Leonard scheme of speed control of DC motor. So that is all for today. Thank you very much.